Good afternoon, everyone, and a huge welcome to UCD's Human Health Impact and Technology series, where we speak to cutting-edge health and technology innovators from across the world. My name is Professor Patricia McGuire, and I'll be your host for this series. The format is that each speaker and I will have a 5-minute chat together, and then we will open up the dialogue to the audience. So please do remember to submit your questions. Today, I have the honor of introducing you to Professor Walter Kolsch. And Walter is the Director of Systems Biology Ireland and the Precision Oncology Ireland Consortium Lead. And I will speak to him about precision oncology and developing digital twins of cancer patients. Welcome, Walter, to the series.
Yeah, hi, everybody. Great pleasure to be here.
Lovely to have you on, Walter. And the first question I have for you today is Systems Biology Ireland and UCD is now one of the biggest childhood cancer research centres in Europe. Can you give us a quick summary of the research that's underway?
Yeah, so systems biology is really a discipline which was born out of the fact that we now can produce so many data, and the bottleneck really has shifted from producing data to understanding them. So what systems biology does is using computer models and mathematical models to analyze biological data. And we're very lucky to have both wet labs where we can do biological experiments as well as computation under one roof. So we can build models, but also then test the models in the lab. And that's a big advantage. And most of our institute is working on cancer. And in particular, we have a big program on childhood cancer. And this is really where we're trying to establish what we call digital twin. And digital twin means computer models of cancer patients, where we, on the computer in silico, can simulate how a tumor arises, how the tumor progresses, how it metastasizes, how it responds to therapy, how it becomes resistant, and what we can do about it. And the idea is in the long term, this is all highly experimental at the moment, but the idea in the long term is that we actually really can do this in the clinic, that instead of giving the patient drugs right away, that we would optimize the treatment on the computer and optimize it to each individual patient so that we can give the best therapy, the optimized therapy to each individual patient. So that's really the gist of it, but there's a lot of research involved, as you can imagine, in order to get there.
And I can imagine that there's so many questions about that. So please do remember to submit your questions if you have any for Walter. But Walter, I want to ask you, September is Childhood Cancer Awareness Month. And I suppose what I've learned from it is that we are fantastic at curing childhood cancer, but there's less awareness about the long-term effects of the actual treatments. And maybe you could tell us a little bit about this.
Yeah, that's absolutely right. So fortunately, we've become really good in treating children with cancer very well, and we have very high cure rates approaching 80–90% in most cancers. However, it comes as a high cost because what we're doing, the mainstay of childhood cancer therapy is chemotherapy, which is genotoxic. It damages the genome. And you can imagine when you damage the genome of small children or babies, there will be long-term side effects, and the list is incredibly long and dramatic. So you can have secondary tumors, hearing loss, infertility, cardiotoxicity, and the list goes on and on. So the big challenge now is maintaining the high cure rates, but reducing the toxicities. And again, this is something where the digital twin comes in, because we also can model side effects, right? And we can anticipate which side effects will affect which patient, and then try to sort of optimize therapy so it still maintains the efficacy, but the side effects are reduced. And we're currently working very hard with our fantastic colleagues in the Crumlin Children's Hospital on a clinical study, which is rolling out, where we develop digital twins in parallel to genome sequencing. So we have a clinical arm where the genome sequencing is used, like it's nowadays used in the clinic, to look at genetic changes. But then we also develop the digital twin models, and we sort of can monitor then in real time what will happen, whether our models are accurate enough, and we can improve our models. And hopefully in 3, 4, or 5 years' time, this actually will then become a tool which clinicians can use.
And is that rolling out in Crumlin Hospital, Walter? That's so
It
exciting.
is, yes. Yes, so we are starting it actually this month. And this is a really exciting, it has been in preparation for many years now, and it's really exciting to actually, see it happening. And it's really a huge team effort, with our clinical colleagues, and there's all of also philanthropy involved, and companies who provide us the reagents for sequencing and doing the sequencing. So it's hugely exciting and a team effort in all aspects.
It's incredible. And Walter, we've so many questions coming in for you. So please do remember to submit your questions so I can get through them all before the end. But Walter, someone's asking about digital twin research in the US on pancreatic cancer. Maybe you could tell us about that?
Sorry, I didn't understand the question.
Oh, I'm sorry. So somebody's asking about your digital twin research that's taking place right now on pancreatic cancer. I don't know, is that correct?
Oh, yeah. We also, the main emphasis is childhood cancer, but we're also developing digital twins for pancreatic cancer and ovarian cancer and other cancers, because the computer models are generic, right? So it's like a computer where you put different softwares on. So once we have the framework, we can run that framework for various different types of cancer. And we do have actually a trial in the States, which is running since 2021 on pancreatic cancer, where we use a digital twin model to recommend therapies. And that trial is currently ongoing.
That's incredible. So there's so many questions, Walter. I'm just so there's a lovely compliment here from you from Martin Kenny. He said, "Thanks, Walter. It's great to hear about the brilliant work being done using the mathematical modeling and systems approaches." And he has two questions for you. So I'll ask one anyway. Can you also model cancer reoccurrence at the site of metastasis? For example, bone metastasis arising after a cure of something like breast cancer.
Yeah, so this is actually one of the areas where we're especially interested in, because therapy resistance and relapses are the big problems in general in all the cancers. This is what patients die from. So we are very interested in trying to model this. At the moment, we are not quite there yet, because that would require more information than we currently have. So what we can model at the moment is mechanisms of resistance. And what we cannot model yet is actually, if there's a metastasis, where it exactly will go to.
Yeah. Okay. And his second question is, have you investigated if or how cancer therapies affect cancer progression? Do certain therapies have short-term positive effects, which then give rise to more aggressive cancer progression?
Yeah, this is an extremely good point. And in particular now with immunotherapies, you often have this phenomenon, or with targeted therapies, that there is an initial really good response and then a rapid progression. For this type, we really ideally would need more data in later time points. And we actually have started not too long ago a clinical study with Austin Duffy at the Mater on pancreatic cancer, where the patients have consented to also receive a biopsy at relapse. And that enables us then to actually to be much more precise about what the mechanisms of relapse are and why the relapse has occurred. So we need this type of longitudinal data to actually, model in detail what the relapse will look like.
Yeah, because your digital twin, I suppose, is just a snapshot in time. Is that correct? And so you'd need to almost keep doing it to understand. So there's another question.
At the moment, we have a snapshot, right? So we are trying to look at a photograph and make a movie out of it.
Yeah, that's a great analogy, actually. There's another question, and actually it's coming in from Donald McKiernan, and he wants to know how is a digital twin defined exactly? For example, is it full genome? Do you look at DNA, just DNA? Is it RNA? Is it protein abundance? Or how do you model your digital twin?
Yeah, so the short answer is the more data, the better, and the more complete we can do it. What we need at a minimum is gene expression data and genome sequencing data. Ideally, we also would like proteomics data and metabolomics data. But we also include, clinical history, and we include existing biomedical knowledge, which we can input in form of knowledge graphs. If you use, the internet, you will have seen knowledge graphs on the internet, which tell you look at this, and then you also likely will be looking at this. So you can actually import existing knowledge in form of graphs into the models. So we can, we're not sort of living in thin air, we're building on existing knowledge as well.
And along those lines, I suppose I'm we've a couple of questions coming in around this idea of snapshot and making a movie. So what about, I suppose, and there's a couple of questions around digital twins getting updated as we age. I mean, are you doing that? Are people actually doing that, Walter?
We are starting doing this. I mean, the digital twin concept actually comes from engineering, when engineers build complex machineries like an airplane or a car. But of course, they can monitor it every second or every minute. So they can constantly update the models. Unfortunately, we don't have that luxury, but what we can do, for instance, the long-term vision would be that as you go to the doctor, as a patient is being treated, that this data will be fed back into the digital twin model so that it's constantly being updated. And that the model learns, as the patient goes through their life journey or goes through their journey in the hospital during the treatment. So updating is important, and this is currently also a bottleneck because, this is something what isn't sort of within the clinical routine. It's not built in yet. So yeah. I hope that changes.
Yeah, and actually something else people are asking about here is this idea of changing therapies, but it's something around compliance to taking drugs and this idea of visualization.
Yeah, visualization is very important because, I mean, if you look at what drives these digital twins, that's very abstract. These are mathematical equations, fairly complicated ones. And in order to actually make it palatable for a human mind, you need to visualize these complex things. And ideally, in the long term, we want this to be like an app on a phone, where you can see, for instance, the effects of the treatment. When you simulate the treatment, you would see your tumor shrinking or growing, and you would sort of visualize actually what's happening in real time. This is something what we are not doing on our own, so we collaborate with companies.
So you could imagine that if you wanted your patients to change their diet or something that would help them progress and help, I suppose, their disease progression, that you could maybe visualize that. Is that correct?
Yeah, for instance. So, I mean, if you think of visualization, there's really the sky's the limit. There's many ways how you can visualize things. I mean, you can see, your weight going up and down, or your blood sugar level going up and down. And I think this is much more effective, right? In particular, when you talk prevention, right? If I show you a number, probably it doesn't make big impact. But if I show you, for instance, your blood sugar going up and your blood vessels clogging up, then there probably will be much more effect.
Oh, I think so.
We're very much used to visual cues.
Yeah, it's good for humans, I suppose, in a way. So, Walter, it's been fantastic speaking to you, but this is so exciting, the developments from your lab, the different projects you're involved in across the world from academia and industry. But I suppose in general, for you as one of the global thought leaders in the area of healthcare, what's the most exciting? What does the future look like for you?
I think what the most exciting is that we really can now get personal, because medicine is all based on population studies. And what we do, we treat the average person. And unfortunately, only very few people are really average. We're all a little bit different. And this is for the first time we really can precisely treat individuals. And I'm originally trained as a medic, and for this it's extremely exciting that you now can be medicine always has been tried to be personal because you have a personal relationship to the patient. But now we actually can be also personal in terms of the science, in terms of the science underlying the treatment and the diagnostics. So this is for me the most exciting aspect.
It's incredible, Andrew. Thank you so much. Digital twins seem to make the risk prediction personal, and that's just wonderful. And it's just such an exciting future ahead of us. And unfortunately, we're getting lots of compliments in on the fact that we are completely out of time. So sincere apologies to all of you whose questions I did not get to. But I wanted to take this opportunity to say a huge, huge thank you to Walter for a stimulating conversation today. Thank you so much, Walter.
Well, thank you, and thanks all the wonderful collaborators we're having on this journey.